So this is example number one for fastener joint stiffness. In this particular problem, I wanted to consider two surface mates. One is made of gray cast iron, the other one is made of steel. And I want to point out that usually when we do surface mates, we want to make sure that they are the same material. In this case, it's a unique case where although this is gray cast iron and steel, they have a similar thermal properties, so that's why we can make them. It's a big concern, especially when you have aluminum and steel. Then aluminum and heat will tend to expand or contract at a faster rate than steel would, and that will bring other issues when you're doing joint analysis. With that said, a tension bolt, you have this problem, and the tension bolt is made by this 1/2 inch 20 UNS. So it's a fine series, unified fine series at 1.5 inches. SAE grade 7, so this is also given, has a standard 1.5 and steel plane washer. The top plate is steel, the bottom plate is gray, and I want to determine the total stiffness of the problem. First of all, before I go ahead and move on, I just want to point out a few things in this problem. Just give me 1 second. So this is where the mate is, but your first through method says that this is going to come right in the middle. Okay, it's the middle from washer to washer. So if I placed another washer down here, then would be washer to washer. Okay, so this will go from here to here and from here to here. However, the materials are different, so I'm going to have to use three separate segments. I'm going to have to find a K for this segment, KM1, let's call it. I'm going to have to find another segment here, call it KM2. I'm going to have to call another stiffness for this segment, call it KM3. Okay, so with that said, let's move on to find the material properties. First of all, this is steel, and if you go to table A5, you can see the carbon steel is actually given 30 MSI, that would be 30 times 10 to the 6 PSI. The gray cast iron is 14.5 MSI, so there will be 14.5 10 to the 6 PSI. So these materials are given. The another thing is I have this. So this just tells you this is your diameter. This is the total length of your fastener. And the second number, it will come from this table. It's a unified series, and that will actually show that this is your N. If you wanted to find your pitch, remember your pitch is 1/N, and that's how you will do that. But let's not worry about that right now. I don't need that in this problem. It's a fine series, so I am working on this side. Is 1/2 inches, so it's right there. And this is nominal diameter. So if I can keep on going down here, this is 20. So I really need from this problem is I'm going to need this information right here to do the problem. Okay, so that's why it's 0.1599 inches squared. That's the information I'm going to use from table 8.2. Okay, so the second thing I want to do is you want to use the assumption of alpha equal to 30 degrees. That's how the first rule method works, unless something else is given. So this angle will be alpha is equal to 30 one side. This is alpha is equal to 30 on this side. Okay, so the total angle here will be 2 times alpha is equal to 60 degrees. Okay, that is the first assumption. So now I want to go ahead and find all these dimensions that I need in the problem. To find the dimensions, this is given in the problem, this right here. That comes from the fact this is 1.5 inches. Another way to also find this, this is for your own knowledge, so you can at least know how we find this if this was not given. Your total L will be this distance plus this distance, right? This is 1.4, sorry, 1/2 plus 3/4 plus your nut. Okay, your nut is 1/4. So this is nut um, plus clearance. Okay, and that would give you a total of 1.5. And in nut and clearance is typically, we like this to be twice this distance as well. So this is 1/8. This will be also 1/8. Okay. This is just for your own information. So where does this come from? This comes from table 8.7. So table 8.7 shared this with us, and you can see that this is 1.5 inches. So this is this case that I'm using here. That's why I say 2 times D plus 0.25. D was 0.5, so this gives you 1.25. Okay? And then these are all definitions given from the table itself. LD will be L minus LD, LT, that will give you 0.25. So this is the total distance from here to here. And LT is this distance, and the distance will be 1.095. Okay, this is important, LD and LT, because I need to know what is the threaded segment in how much, what is the engaged threaded section, and what is the LD engaged uh, unthreaded portion, or the shank portion, to find my stiffness of my bolt. Okay, so let's move on now. The second thing I want to do is I want to go ahead and find what my stiffness is. So this information I know, and this gives you E is steel. How do I know it's steel? This is SAE grade 7, so that's steel. So the property of steel is 30 times 10 to the 6. Your area is given by the table, 0.1599, and you divide this by LT. We found the LT here. This is 1.095. 1.095, and this whole thing gives you 4.3808 times 10 to the 6 pound inches. Okay, this is the threaded portion. Okay, now we want to find the unthreaded portion, and the unthreaded portion is given by D. Remember, your D is equal to 0.5 inches. How do I know that? That comes from your table. Okay, it comes from here. I know this is 0.5, also comes from the table, is 0.5. So that's the value I'm using here. And this is also, it's the same material, it's steel. So this will be this AD gives you pi times 0.5 inches squared divided by 4. That gives you 0.963 inches squared. So this will be 0.9, 0.1963 30 10 to the 6 divided by LD. Your LD was here, that gives you 0.25. So this is 0.25. Do the math, you will get this is 23.562 times 10 to the 6 pound inches. Okay, so your bolt stiffness, then remember this comes from KB is going to equal to KD plus the threaded area. Okay, then I can take the inverse of this, and that's how I find that this is equal to the following expression. This is the same as 1 over 1 over KT plus 1 over KD, or you can also write it in another way, but I only have these values. This is an easy way to use the equations. But this is another variation of this equation, very useful, so you don't have to do all the calculations all the time either. LD plus AD LT, and this will be 3.694 times 10 to the 6 pound inches. Okay, so this is the bolt stiffness. Now I need to find what would be this is the bolt stiffness. I need to find my member stiffness. Okay, so the member stiffness, as I told you, I'm going to divide this in three parts because the half of this portion is there. And again, I want to point this out. Let's suppose I had another washer at the bottom. In that case, this would be this distance over this distance divided by 2, okay? So if that was the case, you can see how this may be shifted even further down, right, for this particular case. Uh, so those are different ways to do the problem, okay? In many problems, we like to put washer at top and the bottom. You saw that in the video because that helps us improves the contact and the clamp force. Okay, so going back to the problem, this is 1 over k, and again, this is if, okay? Um, Hypothetical case, not for this problem. So this is 1 over km1 plus 1 over km2 plus 1 over km3. So you did that. So now I need to find each one of these guys, and then I will be able to solve this. Um, the first case I want to do in this problem is, so the upper portion, the upper portion of this problem is, it tells me that this is uh, grade cast iron. So grade cast iron has 11.5. And the thickness from here to here uh, will be 0.5. So this was, if you remember your problem, this was 1/2 inches plus the distance of the washer. Okay, so that's how I got this value. And your diameter is just this. This big D is not it's not this diameter. Okay, this is your D. That's your small d. Okay, that is your bolt diameter 0.5, or a clearance diameter if you have some clearance. Let's suppose it's tight fit, so we would keep it at 0.5 inches. And then your washer diameter is 0.75. And what you want to do is you want to find the smallest distance from between these 2 points. Okay, so if you would, the problem is actually something like this. Okay, and this is 0.75. This distance I do not know. This is 1/2. This is the washer. We're going to assume that the contact here and the washer is the same. That's a good assumption. So I don't care for this distance. I'm going to use the smallest anyways. Okay, and the T is given by this value, E is given by this, and alpha is equal to 30 degrees. So in this problem then km1 is equal to 1.0574 times 10 to the 7 pound inches. Okay. Now let's go to the small segment. When I do this small segment, I need to do some, first of all, this distance right here is geometry. You take all, you can do the dimensions, you know that this is 3/4, and you can do subtraction and you can find that this is the value you get, okay? And this is the same, the before we continue, we have to go one step back. This value should be 30, okay, 10 to the 6. So this value is going to change. This will give you 3.080. And then this value right here, after you evaluate and you plug in all these numbers, this value comes from geometry because you want to know this distance right here, okay? And that distance is going to come, so do a little bit of geometry here. This is 30 degrees, and you know the height here, right? So you know this value. You're working it here. This is what you're looking for, and you know this height, so you can do yeah, many ways you can find this, but this is one of them. So this is what 4.437, and this is half of it, by the way. So the value that you get for this stiffness is 28.555 10 to the 7 pounds, inches, and then you continue. This is again is 14.75 because this is the same material. This material is steel. That was the mistake. It was supposed to be 30 because it's steel. This is gray cast iron, and this is gray cast iron. And the value that you find here, the thickness from here to here is uh, 0.6725, and then you would use the smallest, and the smallest will be the same value that we began with unless there's another washer. In that case, this will give you a value, if I plug in all these numbers, of 1.415 10 to the 7 pound inches. So your total stiffness member, again, just remember this is springs in series. So this is basically the summation of the inverse of all the springs, if you would. And then this becomes 1 over km1, the inverse of this, plus 1 over km2, plus 1 over km3, and this gives you 9.378 times 10 to the 6 pound inches. And this gives you a total spring constant of, um, you replace the values in here, you get 0.2826. So this is the value that we are looking for, the joint stiffness constant. You can see the value is bigger than 0 and less than 1, so it is acceptable. So this completes example number 1 on fastener joint stiffness.